Good day everyone, I am Danica Joy C. Pejadero, BSED 1, major in English, batch 4, and you can call me Mika. And for today's video, let's talk about the three mathematicians and also their contribution in the mathematics world. The first mathematician is Marshall Hall. He published his famous text theory of group. Marshall Hall Jr. He born on September 17, 1910, and he died on July 4, 1990. Marshall Hall was an American mathematician who made significant contribution to group theory and combinatorics. Marshall Marshall Hall showed a talent for mathematics at a young age, for at age 11, he constructed a seven-place table of logarithm for a positive integers up to 1000. He entered at Yale University as an undergraduate, and there he took many advanced courses in topics such as calculus of Baratians and algebraic number. Marshall Hall graduated with a BE in 1932, having won a prize in every one of his year at university. Marshall Hall at Cambridge, he was taught by several mathematicians who were to have an important influence in him, such as Philip Hall, Harold Davenport, and G.H. Hardy. Marshall Hall wrote his first paper entitled Quadratic Quadratic Residues in Factorization, which is he submitted to the Bulletin to American Mathematician Society in March 1932. While he was in Cambridge, G.H. Hardy helped him edit the paper, which was published in 1933. Hall wrote an introduction. It says there, the purpose of this paper is to establish a certain theorem which is useful in a factorization a large number. Marshall Hall have liked to continue to undertake graduate work at Cambridge, but since the fellowship was only for 1 year and his family could not support him financially, he applied for an actuarial position back in the United States. He was offered a position with an assurance company in St. Louis, which he accepted and began to take actuarial examination so that he might qualify as an actuary. In the spring of 1934, he received two offers in consecutive days. One was for a position he had applied for the Metropolitan Life Insurance Company, while the other was the offer of a fellowship at Yale for graduate work, for which he had not applied. He accepted the offer of a fellowship at Yale, and he was awarded in doctorate in 1936 for his thesis an isomorphism between linear recurring sequence and algebraic rings. His officially thesis advisor was Einstein Ori, but he received a great deal of help and advice from Howard Theodore Engstorm in 1902 and 1962. While at the Institution for Advanced Study, Hall received offer of an instructorship in mathematics from Columbia University and a small similar offer from Yale University. He accepted Yale and began working there in the autumn of 1937. The second mathematician that we tackle in this moment is Ernest Zermelo, a axiomizes set theory in 1908. Zermelo's axiomatization of set theory, first published in July 2, 2013. The first axiomatization of set theory was given by Zermelos in 1908, which became the basis of the modern theory of sets. This theory focuses on the 1908 axiomatization. A further entry will consider later axiomatization of set theory in the period of 1920 to 1940, including Zermelo's second axiomatization in 1930. The first axiomatization of set theory is the axioms. The introduction of Zermelo's paper makes it clear that its set theory regarded as a fundamental theory. The axioms is the theory is that the branch of mathematics whose task in the investigate mathematically the fundamental notion, number, order, and function taking them in their pristine simple forms and to develop thereby the logical foundation of all arithmetic and analysis. Thus, it constitutes an indispensable component of the science of mathematics in 1908. This is followed by the acknowledgement that it is necessary to replace the central assumption that we can assign to an arbitrary, logically definable notion, a set or class, as its extension. In 1908, Zermelos goes on. In solving the problem this present, we must, on the one of hand, rethink this principle distilled from the actual operation with set sufficiently to exclude all contribution, and on the other take them sufficiently wide to retain all that is valuable in this history in 1908. There are 7 types of axiomatry of set theory, and that is extensionality, axioms of elementary set, separation, power set, union, choice, and infinity. First is extensionality. This says roughly that sets are determined by the elements they contain. Second is axioms of elementary set. These arrest A, the existence of a set which contain no members, the existence for many objects A of the singleton set A, which has A as its sole member, and C, and the existence for any two objects A, B, of the unordered pair A, B, which has just EB as set members. Third is separation. This asserts that for any given set A and any given definite property of elements in, one can separate out from A as a set just those elements which satisfy the given property. The fourth is power set. This say that for any set, the collection of all subsets of that set is also a set. Union is the fifth union. This say that for any set, the collection of the member of that set also from the set. 6 is choice. This says that for any set of pairwise disjoint non-empty set, there exists a set which contains exactly one member from each member of the given set. The last is infinity. These final axioms assert the existence of infinitely large set which contain the empty set, and for each set A that it contain also the set A, thus this infinity set must contain. The four central axioms of Zermelo's system are the axioms of infinity and power set, which together show the existence of uncountable set, the axioms of choice, to which we will devote same piece below, and the axioms of separation. The problem of the axioms as separation is not with the obviousness of the principle. It seems straightforward to accept that if one has a set of objects, one can separate off a subclass of this set of specifying the property, and treat this in turn as a set. The question here is a subtler one, namely that of how to formulate this principle as an axiom. What means of separating off or are to be accepted? What are allowable as the properties? As a matter of practice, we use language to state the properties and informal mathematics. This is a mixture of natural language and specific mathematical language. There were also a problem with the completeness of Zermelo's theory, since there were important theoretical matter with which Zermelos does not deal, either for want of appropriate definitions, showing how certain construction can be represented in a pure theory of set, or because the axioms set out of Zermelo's system are not strong enough. Zermelos gave no obvious way of presenting much of ordinary mathematics. The last mathematician that we tackle in this moment is Andrew Wiles. He proves of Fermat's last theorem. He is a British American. Andrew Wiles is a special case of modularity theorem of elliptic curves, together with the Ribet theorem. It proved a fruit of Fermat's last theorem. Both Fermat's last theorem and a modularity theorem were almost universally considered inaccessible to proof by contemporaneous mathematicians, meaning that they were believed to be impossible to prove using current knowledge. Andrew Wiles announced his proof on June 23, 1993, at a lecture of Cambridge entitled Modern Modular Formats, Elliptic Curves, and Gaussian Representation. However, in September 1933, the proof was found and contained an error 1 year later, on September 19, 1994, in what he would call the most important moment of working life. Wiles stumbled upon a revelation that allowed him to correct the proof of the satisfaction of the mathematical community. The correct proof was published in 1995. Andrew Wiles' proof used many techniques from algebraic geometry and number theory, and has many ramifications in these branches of mathematics. It also used standard construction of modern algebraic geometry such as category of Chimiz and Iwasawa theory, and other 20th century techniques which were not available to Fermat. Are mathematicians finally satisfied with Andrew Wiles' proof of Fermat's last theorem? Why has this theorem been so difficult to prove? So, Fermat's last theorem was until recently the most famous unsolved problem in the mathematics. In the mind of 17th century Pierre de Fermat wrote that no value of n greater than 2 could satisfy the equation of x power of n plus y, n minus zn, where n, x, y, and z are all integers. He claimed that he had a simple proof of the theorem, but no record of it has ever been found. I've seen that time countless professional and amateur mathematicians have tried to find a valid proof and wondered whether Fermat really even had one. Then, in 1994, Edward Wiles of Princeton University announced that he had discovered a proof while working on a more general problem in geometry. Fermat's last theorem is also called Fermat's Great Theorem, the statement that there are no natural numbers in 1, 2, 3, and the rest, x, y, and z, such as that xn plus xyn equals zn, in which n is a natural number greater than 2. For example, if n equals 3, Fermat's last theorem states that a natural number x, y, and z exists such that 3x plus y3 equals z3. His work was one of the most stunning results in the modern mathematics, and now he's won one of the biggest prizes in the field. Andrew Wiles of the University of Oxford, who in the 1990s cracked the long-standing mystery of Fermat's last theorem, has been awarded the 2016 Abels Prize. Fermat's last theory was a seemingly simple puzzle posed on 17th century mathematician Pierre de Fermat. He said that for any three whole number a, b, and c, the equation an plus bn and cn could not be satisfied by any whole number n greater than 2. What's more, he claimed to have a proof for a theorem that could not be the content of the narrow margin of the textbook he happened to be scrambled in. Will also in Scientific American work, I believe he has had some good idea in trying to construct the proof that the proof is not there. To some extent, proving Fermat's theorem is like climbing Everest. If a man wants to climb Everest and falls short of it by 100 yards, he has not climbed Everest. In fact, from the beginning of 1994, Wiles began to collaborate with Richard Taylor in the attempt to fill the holes in the proof. However, they decided that one of the key steps in the proof using methods thought to flush could not be made to work. On October 6, Wiles sent the new proof to three colleagues and include fillings, all like a new food, which was essentially similar than the earlier one. Fillings sent a simplification of part of the proof. No proof of the complexity of this can easily be guaranteed to be correct, and a very small doubt will remain for some time. That's all for today, and that is the three mathematicians and also their contribution in the mathematics world.